And maybe in some cases you use the, for example, in-serve model. QoS, let me to emphasize that while in-serve provide the highest guarantee of QoS, it is very resource intensive and therefore not easily scalable. In most cases, we don't use in-serve in normal networks. Okay, we are using differentiated service or diff-serve that I will explain it. But if you want, you can use the in-serve in one network. In most cases, we are using differentiated service. Let me to show you one picture. This figure can help you to understand about the limitation of the in-serve and about the problem of the in-serve related to the scalability. As you can see here, we have 4 computers on the left side and 4 computers for receivers on the right side. Each computer in the left side has at least one application that is trying to reserve the required resources. Because of that, each of them should send RSVP pass message. This RSVP pass message should be sent to the right side to the receivers. And as you can see here, we have multiple RSVP pass message. They are sending from the pass that the data, okay, should be sent. And actually we are using the resources in this pass. Then we are receiving RSVP reserve message, again multiple RSVP reserve message, and here we have many states in each device that we should for example save for the in-serve model. The detail of this RSVP pass state is not important, but here you can see that for example in one line we have a state for the traffic with this source IP address to this source IP address, the protocol, destination port, source port, destination, and previous hop, and also the required bandwidth. Actually here we need signaling before sending the traffic. Maybe it is adding the delay to the forwarding of the traffic. For example, the computer 1 needs to send traffic to the computer 2, okay, and first it should signal the pass, after that it can send the traffic. It means that now here we have one more delay in this model. Actually, we can say in-serve model is a good model in special cases, and in most cases we don't use the in-serve model and we are using the differentiated service model. Actually, we can say diff-serve was designed to address the limitation of the best effort and also in-serve model. With this model, there is no need for a signaling protocol and there is no RSVP flow state to maintain on every single node, okay, which makes it highly scalable. This method, differentiated service, is a highly scalable. Actually, in this method, in the diff-serve model, we are implementing quality of service techniques in each node. Let me to explain a little more about the differentiated service model. When we are using differentiated service or diff-serve model of quality of service in one network, actually in each router we should independently configure the quality of service tools. Let me to explain one simple scenario for better understanding it, but in this class we will learn more than this about the differentiated service model. Assume that here we have 2 types of traffic. For example, the first type of traffic is data traffic, and also the second type of traffic that now we have here is the VoIP traffic. And you know that VoIP or voice over IP packets need the priority, okay, and also we should guarantee the bandwidth each of these traffics needs. For example, here we need 1 megabit per second, or we have 1 megabit per second of bandwidth in the link between the router 1 and router 2, and also in the router 2, in the link between router 2 and router 3, okay. We want to give about 800 kilobit per second of bandwidth to the data, okay, and also 200 kilobit per second of bandwidth to the VoIP. Actually, VoIP doesn't need so much bandwidth, but you know that VoIP needs the priority, because for VoIP packet the delay and jitter is so important for us. Okay, how we can implement these policies with the differentiated service model? Look at here. In the differentiated service model, first we should identify the traffics. Okay, for example, in the router 1, in the first hop, this is the first hop, okay, we are configuring some traffic classes. For example, here we are configuring two classes, the class 1, okay, and also the class 2. In class 1, we are using some tools for identifying the traffic of data. Actually, we have the traffic of data, for example, according to the source port, destination port, IP address, or some other things. Also, in the class 2, we are identifying the traffic of VoIP, okay, and after that, in most cases, in the router, in the first device, we are marking the traffic. Why we should mark the traffic? Because in other devices, for example, in the next device, router 2, router 3, they can easier understand that this traffic is received from which type of traffic, which class, which traffic class actually, okay? You will learn about the detail of mark. After that, here we are giving the specific bandwidth to each type of traffic. For example, here we will give the bandwidth of 800 kilobit per second, 800 kilobit per second to the data, and also the bandwidth 200 kilobit per second to the VoIP, okay? Also here we are configuring some tools that with those tools we can give priority to the VoIP. What does it mean? It means that if we have 1 megabit per second of the data and VoIP, first we should give 200 kilobit per second of the bandwidth to the VoIP, and after that we should give 800 kilobit per second of bandwidth to the data. This is our policy in the first hop. Again, in the second hop, we should configure the next policy. Here we don't have any signaling protocol because of that this is a scalable protocol, a scalable mechanism, the differentiated service model. Here again we have, for example, class 1 and class 2, but in the class 1 we don't need to, for example, classify traffic according to the port, to IP address, or some other things. Here we are classifying the traffic according to the mark that we have used in the router 1. Because of that, here we are using the mark for classifying the traffic. Again, we will configure the bandwidth and also the priority bandwidth for different type of class. And finally, in the router 3 also we have similar condition. Actually, we can say when we are using differentiated service model, as you can see from the name of this model, you can understand we can configure different policy in each hop. In most cases, these policies is according to each other, but if you want, you can configure different policy in each of these devices. Because of that, in some cases, maybe you see the term per hop behavior. Actually, in each hop we can configure different behavior, and this is the method that we call it differentiated service model. Actually, differentiated service is not an end-to-end QoS strategy because it cannot enforce end-to-end guarantees. However, DiffServ QoS is a more scalable approach to implementing QoS. Unlike IntServ and hard QoS, in which the end host signal their QoS needs to the network, DiffServ does not use signaling. Instead, DiffServ uses a soft QoS, not hard QoS approach. It works on the provisioned QoS model, where network elements are set up to service multiple classes of traffic, each with varying QoS requirement. Also, the differentiated service or DiffServ QoS model specifies a simple and scalable mechanism for classifying and managing network traffic. For example, DiffServ can provide low latency guaranteed service to critical network traffic such as voice or video, while providing simple best effort traffic guarantees to non-critical services such as web traffic or a file transfer. And the DiffServ design overcomes the limitation of both the best effort and IntServ model, and because of that, in most cases we are using the DiffServ in today's network. DiffServ can provide an almost guaranteed QoS while still being cost effective and also scalable. Let me to explain it again. Look at here. As a host, forward traffic to a router, for example, C1 to the router classifies the flows into aggregates or classes and provides the appropriate QoS policy for that class. diffserv enforces and applies QoS mechanism on a hop-by-hop basis, uniformly applying global meaning to each traffic class to provide both flexibility and scalability. For example, diffserv could be configured to group all TCP flows as a single class and allocate bandwidth for that class rather than for the individual flows as intserv would do. Okay. In addition to classifying traffic, diffserv minimizes signaling and state maintenance requirement on each network node.